So here I'm going to talk about the question in thermal and statistical mechanics which appeared in GATE 2014 examination. So let's continue with the first problem. The question is, for a gas under isothermal condition, its pressure P varies with volume V as so the given relationship, that is pressure, it is proportional to B power minus 5/3. Okay, or we can write pressure that is equal to some constant of proportionality and then V power minus 5/3. So let's call this as equation 1. The bulk modulus B is proportional to, so it's known that the bulk modulus, it's connected with the compressibility. So this relationship where kappa T is the compressibility, isothermal compressibility. Now kappa T, this is equal to the fractional change in volume. Okay, so it's compression, so that means it's respect to pressure, and the condition is that it's isothermal. Okay, a negative sign is introduced here just to keep it a positive quantity, because dP by dV it's going to be a negative quantity, so ultimately this will make it a positive quantity. So therefore these two relationship, they allow me to write that the bulk modulus of elasticity, that is B, that is equal to minus B dP by dB at constant temperature. Okay, now with the help of equation 1 and 2 I will evaluate to dP by dB and then substitute it back into equation 2. So dP by dB at constant temperature, so that is equal to curly B of CB power minus 5/3, and that is equal to minus 5/3 C B power minus 5/3 minus 1. So therefore B is equal to, that's bulk modulus, that is equal to minus V into dP by dV, that is multiply by minus 5/3 C B power minus 5/3 minus 1, so that is equal to 5/3 C B power minus 5/3. So therefore from here we conclude that the bulk modulus of elasticity, that is proportional to B power minus 5/3. So therefore D is the correct option. Let's take a look at the next problem. So we are given that at a given temperature T, the average energy per particle of non-interacting gas of two-dimensional classical harmonic oscillator is how much? Okay, so if you just recall that for a two-dimensional harmonic oscillator, for a two-dimensional classical harmonic oscillator, its energy values are given by the Hamiltonian, you can say, that is equal to, it's a two-dimensional, so therefore we will have two momentum term, px square plus py square divided by 2m, where m is the mass of the oscillator, plus the potential energy term, half k x square plus y square, but note that here it's k, it's the spring constant, or the force constant, you can say spring constant or force constant. Now if you take a look at the expression 1 here, so had it been a one-dimensional oscillator, then we will have only one kinetic energy term and one potential energy term. Okay, but here because it's a two-dimensional harmonic oscillator, so that's why we are having two kinetic energy term and two potential energy term. Okay, so in total we are having 4 square energy term. Okay, so now according to the equipartition theorem, each square energy term contribute to the average energy, that is equal to half kVT. So because we are having 4 square energy terms, therefore the average energy of the harmonic oscillator, because of the presence of these 4 square energy terms, that will be 4 multiplied by 1 by 2 kVt, and that is nothing but that is 2 kVt. So therefore our answer is 2 kVt. So let's take a look at the next problem. So it is which one of the following is a fermion. Okay, so let's try to figure out that which one is a fermion. Okay, so alpha particle is nothing but it's the helium nucleus, and it consists of, the helium nucleus consists of 2 proton plus 2 neutron, and that is equal to a sum of these nucleon, that is a even number, because proton, electron, proton and neutron, all of these particles, they are half integral spin particle, half integral spin particles. Okay, so when they are present in even number, so that means their net spin will come out to be a even number basically, or the integral, sorry. Okay, but when they are present in odd number, so their sum of the spins, that will be a half integer. So accordingly we can classify them as a fermion or boson. Okay, so alpha, it's first is the alpha particle, and second is the 4 VE7 nucleus. So it's because it's a nucleus, so that means we simply need to evaluate only the nucleons or the mass number. Okay, so mass number here it's 7, so that means it's having 4 proton plus 3 neutron, and that is equal to their sum is equal to an odd number. Okay, now let's take a look at the hydrogen atom. Hydrogen atom means it's protium. Hydrogen atom, it's a protium. Okay, so it consists of 1 electron plus 1 proton. And the sum is a even number. It's an even number. Now deuteron. So deuteron, it's a nucleus of deuterium. Okay, so that is deuterium nucleus. Okay, that is nucleus of 1H2. So it will consist of only 2 nucleon, that's 1 proton and plus 1 neutron, and that is equal to an even number. So as I said here, electron, proton and neutron individually, they are having half integral spin, but when they are present in the even number or an odd number, so accordingly we can call them as the boson or fermion. So here even number, that will lead to the conclusion that it's a bosonic particle, it's a boson. So it's an odd number here for VE7, it's an odd number, so that means it's a Fermi particle. Okay, so here hydrogen atom, it's an even number, so that means it's a boson. Okay, again deuteron, so it's a nucleus of deuterium, it's again it's having even number of nucleons, so therefore it's a boson. Hence it's the option B, that's the correct here. So now let's continue with the next problem. For the system of 2 boson, each of which can occupy any of the 2 energy levels. So we are having a system of 2 boson where they can occupy the given 2 energy levels. Okay, so let me first draw this the energy level. The mean energy of the system at temperature T. So we can obtain the mean energy by making use of the partition function approach. But before writing a partition function, we must have the idea about the different microstates that a system can have. So we have 2 boson, N is equal to 2 boson, and we are having a 2 energy level system. So let me first draw the microstates that this system can possess. So because on the boson there is no condition on the occupancy, so they can stay together or they can also stay separately. So not 3, not 4, but we will have only 2 microstates. Okay, 3 microstates, sorry, 0 E. So here the energy will be 0, and here it is 2E, and here it is E. So therefore the partition function for this system will be Z, that is equal to exponential minus beta EI. So accordingly EI, it's having 0, 2E and E value. So we get 3 terms in the partition function. So our partition function is 1 plus exponential minus 2 beta E plus exponential minus beta E. And from here we can calculate the average energy of the system E, that is equal to minus curly beta of ln z, and that is equal to minus curly beta of ln 1 plus exponential minus beta E plus exponential minus 2 beta E. Okay, and that is equal to minus 1 upon 1 plus exponential minus beta E plus exponential minus 2 beta E, and then again the differential of these two terms. Okay, so that will give us exponential minus beta E and then multiply by minus E plus exponential minus 2 beta E multiply by 2E. Okay, so ultimately we obtain that average energy of this system, that is equal to, because here we are having minus and minus here, so outside we also having minus, so that will cancel with each other, so ultimately we will get a positive sign. So the average energy turns out to be exponential E exponential minus beta E plus 2E exponential minus 2 beta E upon 1 plus exponential minus beta E plus exponential minus 2 beta E. And if we just take a look at the options that are given to us, so none of the option matches with the result that we have obtained, but there is nothing wrong in the result that we obtained. So none of the option match with the result. So let's continue with the next problem. The statement is, consider a system of 3 fermions which can occupy any of the 4 available energy states with equal probability. The entropy of the system is, okay, so in order to calculate the entropy of the system, we must first calculate the available microstates to the system, okay, because we are having 3 particles and we have to distribute all these 3 particles in 4 different energy states, okay, here for instance as shown here in the diagram. So I have drawn these 4 respective microstates here. So accordingly, because it's a system of fermion, so the Pauli exclusion principle will be valid here. Pauli exclusion principle, okay. So that's we have to ensure that a single particle energy state contain only one fermion, okay. So this way we notice that the total number of microstates, that's omega, that is equal to 4 here. So according to the Boltzmann definition of the entropy, the entropy is given by S is equal to Kb ln omega, and that is equal to Kb ln 4, okay, and that's nothing but that is equal to 2 Kb ln 2, okay. So therefore option B is the correct option here. So let's take a look at the next problem. The statement is, a particle of mass m is subjected to a potential Vxy, that is equal to 1 by 2 m omega square x square plus y square, where x ranges from minus infinity to infinity and y ranges from minus infinity to infinity. The state with energy 4h cut omega is G4 degenerate. The value of G is how much, okay. So first let's write the expression for the energy eigenvalue for the this two-dimensional harmonic oscillator. The corresponding energy eigenvalues, that is E, Nx, Ny, that is equal to Nx plus half h cut omega plus Ny plus half h cut omega. So here we have assumed that the motion along x and y direction, it is independent from each other, so that the Nx and Ny, they can have value 0, 1, 2, 3 and so on. Okay, so this energy spectra can also be rewritten as E, Nx and Y, that is equal to Nx plus Ny plus 1 and then h cut omega. So we are given that the condition that Nx plus Ny plus 1, that should be equal to 4. Okay, so that the energy is 4 h cut omega. So this implies that Nx plus Ny, that is equal to 4 minus 1, that is equal to 3. So we have to accordingly choose the values of Nx and Ny so that their addition is 3. Okay, so let's see how many combinations we obtain for Nx and Ny such that Nx plus Ny, that is equal to 3. Okay, so the possible values are 0, 3, and this will be 3 in that case, 3, 0, so that will give you 3 here, 1, 2, 3, 2, 1, and that will also give us a value of 3. So therefore we are having a G is equal to 4. That's a degeneracy for the energy equal to 4 h cut omega, the two-dimensional oscillator. The corresponding degeneracy is 4. So 4 is our answer here. Let's take a look at the next problem. For the free electron gas in 2 dimensions, the variation of the density of state Ne as a function of energy is best represented by. So for this purpose we must have an idea about the variation of density of state with the energy, and this can be quickly calculated as below. For the two-dimensional 2D electron gas confined in a system whose area is area is equal to A, or in simple word we can choose area that is equal to L cross L, a two-dimensional box of length L. Okay, because the electron gas, it's a non-relativistic system, so that means the corresponding energy of the electrons inside the metal two-dimensional system can be written as E, that is equal to P square upon 2m, where P square is equal to Px square plus Py square. Okay, then the number of microstates with momentum less than equal to P, okay, omega P, that is equal to the area available in the ordinary space and then multiply by the area available in the momentum space, and then the area occupied by one unit cell, that is h square. Okay, so that will give us the number of microstates here. Okay, so from here we can calculate the number of microstates or the energy states with momentum ranging from P to P plus dP, and that is equal to d omega P upon dP multiplied by dP, and it comes out to be equal to, so from here we will have 2p dP. Okay, from here, so that means this is equal to 2 pi A upon h square p dP. Now this expression can be transformed in terms of energy as below: omega dash E, that is equal to 2 pi A upon h square p dP. Okay, so because the relationship between momentum and energy is P square, that is equal to 2me, so this will give us 2p dP, that is equal to 2m dE. Okay, so our p dP is equal to mdE, so here I am replacing it with m dE. So this gives us the number of states with energy range E to E plus dE, and it is denoted by GE dE. Okay, so that means GE dE, that is equal to 2 pi A upon H square, and then multiply by M, and then E power 0, because there is no energy dependence, so that's why I'm writing it's E power 0, and then dE. Because the density of states in 2 dimension, they are independent of energy. They are independent of energy. So that means when it's a simply constant, some constant value. Okay, so therefore the best representation is given by option C here. So option C is the correct one here. So let's take a look at the last problem. So the statement is the plot of specific heat versus temperature across a superconducting transition. Temperature Tc is most appropriately represented by, okay, so we should recall that the superconducting transition, the superconducting transition is a continuous transition of second order. Continuous transition of second order. Okay, so there is no latent heat. No latent heat. And no significant step change in entropy. However, a step in heat capacity is observed at superconducting to superconducting to normal metal transition. So that is at T is equal to Tc, a step in the heat capacity is observed, and this is best represented by option A. So option A is the correct one here.